Hi, in this video I'm going to talk about what is Poisson regression and how to build a Poisson regression model. So this is basically used for modeling count data. So we'll see how we can use Poisson regression to model count data. If you haven't subscribed to our channel, please subscribe to our channel. Okay, so in this session, we'll first see the theory behind Poisson regression model, and we'll also see what are the uses of Poisson regression models. You can use this type of modeling technique in a variety of real-world problems. We'll see what are these problems you can actually solve using Poisson regression model. We'll take an application using R. We'll take an use case to understand how we can actually use this modeling technique. Alright, so let's start with the introduction. Well, Poisson regression models are used to model count data. As I've said in the first slide itself, that we are interested in using this model in scenarios where the data that we have is nothing but count of something. So the dependent variable or the target variable is a count of something. Okay, you mean what? So what are the examples of such cases? Well, the examples could be the number of visits to a website by a user. Okay, so that could be a count, right? Count of hours won by a student, that could be another example. Count of death in a hospital in a year, number of accidents taking place, number of calls to a call center, number of flu or typhoid cases in an area, number of car or truck that crosses a particular breeze or express. So these are typical cases or typical examples of a count data dependent variable or target variable. So what are the features of a count data dependent variable? Well, a count of something is always positive, right? Count of something cannot be negative. So that's one feature. The second feature is that count can take 0 as well. So count of something could be 0, right? So many times in this particular type of data, we'll have so many zeros in the target variable. And that's interesting because if you have so many zeros in the dependent variable, then you need some special technique to model that, because count of something, for instance, let's say count of death in a hospital, it could be 0 in a particular or in a given time period, right? There could be no death at all, and that cases are pretty large in number in many cases, and that's why something else has to be done. I mean, in a typical linear regression, you wouldn't come across so many zeros in a dependent variable. All right. All right. So, and it can be 0, and then it can go till infinity. Okay, but it can't be a negative number. So it is it has a lower bound, right? This is a lower bound, right? All right. So this we'll keep this in mind while building this model. Every time we face scenario like this. All right. So we assume here that the dependent variable is having a Poisson distribution. Okay, so you may be familiar with what a Poisson distribution is. If you're not familiar, we will have a brief overview of what Poisson distribution is in the next slide. So the motivation behind Poisson regression model is coming from the Poisson distribution. So we assume here is that the dependent variable or the target variable follows a Poisson distribution, Poisson probability distribution. Okay, and one of the feature of this distribution is that it is always used for numerical and continuous data. Okay, so that's one thing to be kept in mind. Poisson distribution is useful to model count and the rate of something. Rate means something happening at a given rate of time. For instance, death per month. Okay, or let's say number of calls per hours. Okay, So the rate of something, if you have something like rate of something, you use Poisson distribution in those cases. Okay, so examples, so I've given quite a number of examples. So other examples could be modeling for road traffic, some incident rates, and so on. So it's very useful actually. It's very useful in finance industry, where you're trying to model for the rate of default in a given period of time. You're trying to model for many of these financial events, like let's say the number of financial crises happening in a given period of time. It's also used in supply chain operation management. Okay, in operation management in manufacturing and supply chain industry. That's where you get to know how many orders are coming in a given period of time, and so on. Okay, so it's heavily application oriented and has a lot of uses in the real world scenarios. The probability mass function, which is the discrete version of the probability density function. So when it is a discrete function, we call that as a probability mass function. Okay, so this is probability is given as this. Okay, so if x is a random variable, okay, and that takes a count of something, let's say for instance count of death in a given hospital, it could be 0, 1, 2, anything, right? Can't be a negative number. Then it is distributed like this, exponential of a parameter lambda, and I'll talk about what lambda is, and then lambda to the power x divided by x factorial. And remember, x is nothing but the count of something. Okay, count of something. Okay, count of number of days, count of number of calls, or something like that. And it is always positive, equal to or greater than 0, because the factorial of a negative number is not possible, right? So that's makes sense, because count can never be a negative number. Okay, so the parameter here, and we are interested in the lambda. Okay, and what is lambda? Well, lambda is the average number of occurrence of an event. And the event here, we have taken it as a death. It could be any other event as well. So lambda is the average number of occurrence of an event in a specified time. Okay, so this is the parameter. So lambda in the case of an example of number of deaths is like, what is the average number of deaths? Average number of deaths, we call that as lambda. Okay, okay, average number of deaths per a given time. Okay, so I'm keeping that silent. Similarly, average number of calls in a given time, that is also lambda. Okay, so that's the parameter we are interested in. Okay, and the actual average number of deaths in a given time can be done by lambda multiplied to the given time, the delta t. Okay, the duration under consideration. Okay, so this is the basic theory behind a Poisson distribution function, or Poisson Poisson probability distribution, and how it can be leveraged to model count data. So we have some idea now. We are not getting into the details of Poisson regression theory. I've just given a brief overview what it is all about, and we'll straight away go ahead with an example and understand how we can use. Okay, here is the graphical view of the probability mass function, and you can see as you increase lambda, so lambda can take it can be 0, 1 in number. Okay, so if you increase lambda, like for lambda equal to 1, we have this red one, lambda equal to 4, this green one, and lambda equal to 10 is the blue one. And you can see that when you increase the value of lambda, a Poisson distribution is becoming more like a normal distribution, right? This is more like a normal distribution, right? So if you increase the value of lambda, you tend to be approaching towards a normal distribution. Okay, few more features of a Poisson regression model or Poisson distribution, to be precise. Okay, the expected value of x or expected value of the random number that is taking count of something is the average or the rate or the parameter in consideration, which is lambda. The variance is also exactly lambda. Hence, mean equal to variance. So this is an important feature of the Poisson distribution. So if in a data, if you see the mean and variance are more or less similar, you can think of using a Poisson regression, a Poisson distribution model instead of a normal distribution model, also to say. I mean, there are of course other tests to be performed before concluding that it is distributed. Uh, it is distributed as a Poisson regression model. However, this will give you some sort of an evidence. So the idea here is to understand whether the mean and variance are same in a given data. And one thing to remember is that the Poisson distribution tends to become a normal distribution as lambda becomes large. Okay. So now we'll learn what theory behind the Poisson regression model. Okay, so we learned what Poisson distribution is, and that's exactly is the motivation. Okay, now any regression model has two things, right? So one is target variable and the set of independent or explanatory variable, right? So basically, any regression model will have something like this is the dependent variable, and we have it's a function of several independent variables. So we are interested in finding out the parameters parameters and the function that relates the dependent variable to the set of independent variables. Now here the dependent variable, as I have said, is a count of something, right? And count cannot be negative. However, the explanatory variable can take any value, right? It can take negative values as well. Now that's a typical problem. That's a problem where you have a restriction on the dependent variable, but there is no restriction on the independent variables. So that is a problem. So you have restriction on dependent variable, right? That it cannot take any negative values. Okay, but there is no restriction as such on the independent variables. Now that will create problems if you use the ordinary least square or the multiple linear regression. If you use that, assuming that it's normally distributed and error terms will be normally distributed, and you're using ordinary least square in this case, it's going to give the answer or the output is going to be problematic because the assumption seems to be somewhat different. Hence, we do one thing. What we do is that we take the logarithm of y instead of y itself, and then we model it in the function of x. Now, how does that help? Well, if we take a logarithm of something, it can take negative values, right? So if I take let's say log of 10 to the power minus 2. Now 10 to the power minus 2 is not a negative number, but if you take a log of that, it is nothing but minus 2, right? So that is a negative number, right? Similarly, if I take a log of 0.002, so 0.002 is not a negative number, whereas the log of 0.002 is a negative number. So by taking the log of the dependent variable, we are getting rid of the restriction that was there before, the restriction on the fact that it cannot take a negative number. Now our left hand side can take negative number, so this particular term can be negative. Okay, and of course there is no restriction on the independent variables. So so that's the idea. That's exactly why we are going to use a log linear model instead of a linear model. So we'll use the log linear model because we have logarithm in the taken in the left hand side of the model. We have taken the logarithm of the dependent variable. And this is a class of model considering the generalized least square. I'm sure you are familiar with other generalized least square models. Multiple linear regression, logistic regression are also part of generalized linear regression models, where the only difference between these models are in terms of the distribution. Otherwise, the estimation is more or less same. We'll use the maximum likelihood to do the estimation. The few assumptions here we have, I think we have already discussed few of them. Just we'll introduce to you y values are count. So that should always be count. Otherwise, there's no reason to use a Poisson regression if it is not a count of something. Okay, count must be positive, so you cannot have a negative numbers. Okay, and it's a discrete distribution. That's one assumption. So it has to be a count of something. It has to be a whole number, 0 or greater than 0. Okay, so the count should be following Poisson distribution. So that's one test you can do before even going out with this model. Just do a brief test, whether it is by taking the mean and variance, or by doing some statistical test. You can actually test whether your data follows Poisson distribution or not. So just take the mean and variance and see whether they're very close to each other or not. If that's the case, then you are good to go with the Poisson regression model. So a bit of more theory. So this is how the regression model looks like. We have log of the count. We have taken it as mu. It could be y, x, whatever you can actually give. And it is a function of a number of x variables or independent variables, and we are interested in finding out the parameters alpha and beta, pretty much like your linear regression models, right? But remember, this is not like your typical log model, log linear model in a multiple linear regression. The distribution itself is totally different, so don't confuse with that. Okay, if you take the logarithm into the right hand side, your mu, or we call that as y also, we can say it y also, y equal to exponential of alpha plus beta x. And when you take an exponential of something, you can actually write in this way: exponential of alpha multiplied to exponential of beta x, right? That's what we have learned in mathematics, where when you have something, two added value is the power of something, they're nothing but the multiplication of the bases, right? Now this is interesting because the normal way of explaining the parameters or interpreting the parameters will not be the same. It has to be different. So what we have learned in a multiple linear regression, interpreting the beta parameters is totally going to be different here. So what is what does alpha says? What is the intercept? How do we interpret the intercept? Okay, so exponential of alpha is the effect of mean of y. Okay, and remember this concept is the mean of y, not y itself. Okay, because we are modeling for the average average occurrences when x equal to 0. So when x is equal to 0, this becomes 1, right? That means your average of x or expected value of x is nothing but e to the power alpha, right? So that's exactly the interpretation. How do we interpret exponential of beta? So that's what we have the exponential beta, right, associated with x. This is nothing but with every unit increase in x, the predictor variable has a multiplicative effect. That means it is not only going to be impacted by the value of what is the value of exponential of beta, it will also get affected by what exactly is the value of alpha as well. That's not the case in linear regression, right? If you have y plus alpha plus beta x, in that case, if you have x increased by 1 unit, the corresponding increase in y is just beta. There is no relationship with alpha, but here there is a relationship because it has a multiplicative effect, because you are multiplying exponential of beta to exponential of alpha. So the marginal effect is not just dependent on the value of beta, it's also dependent on the value of alpha. Okay, so that's why it is different. But in a multiple linear regression, that's not the case. It's only the beta values that matters while explaining the marginal effect. Okay, there are a few more interpretation. I won't get into the details, but just briefly I'll talk about if beta equal to 0 and then exponential of beta is 1, right? So this becomes 1. So the expected count of y, the expected count and y and x are not related. That means every time you have a beta of 0, the model itself is of no use because they are not related at all. The explanatory variables and your dependent variable or target variable, they are not related. So there's no point in going ahead with the model. However, it can be greater than 0 or less than 0. And how do you interpret when it is greater than 0? If exponential of beta is greater than 1, and remember exponential of beta, we are talking about e to the power beta is greater than 1, then the expected count, okay, or the average of the dependent variable, which is nothing but expected value of dependent variable, is exponential of beta times larger than when you had x equal to 0. Okay, it's slightly tricky to understand, but if you think for a while, you can easily get it. Okay, so we're comparing it with the first condition, right? We talked about in the first condition, in the condition number 1. So condition number 2 and condition number 3, we're simply comparing it with the 1. If x equal to 0, what is the effect? And if exponential, x is not equal to 0, and the case is that your exponential of beta is greater than 1, how is it related to the first condition? And similarly, we can also compare the third one. Okay. Slightly complicated, but yeah, if you think for a while, you can always get it very easily, not an issue. So one thing to remember is that it has a multiplicative effect. That means you have alpha beta together impacting your dependent variable. In contrast to your multiple linear regression where they were impacting independently or differently, separately. All right. So we'll take an implementation. We'll use a problem and we'll solve it using R. So Poisson regression is estimated using maximum likelihood, pretty much like most other GLM models. So the one technique that is used is maximum likelihood to find out the estimates. We'll use the GLM function in R. It's part of the mass package. So if you haven't downloaded, you can download and install it and get it on your R so that you can use to build the model. Okay, so here is an example. So we're going to use an example that is there in one of the website. I'm going to give you the link to the website. So here is the case where we're trying to find out the number of awards you earned by students given their certain attributes, and the two attributes we have been given is that the program to which a student has been admitted to, and the score on the particular students on mathematics. Okay, so we'll see the data and it will be clear. Okay, so we're trying to predict. So yeah, dependent variable y is nothing but the number of awards won by the student, and we have two explanatory variable. X1 is the program is 1 2 3. One is I guess vocational, the second one is general, and the third one is academic, and the second explanatory variable is the score in mathematics. Okay, so how does this two explanatory variable is impacting the average number of awards owned by students? Okay, so we are interested to know that. So we'll we'll import the data set, and it's there in the University of California, Los Angeles, UCLS website. You can it's publicly available, so you can import it on your R session. Okay, so there are three variables. One is a dependent one, the number of awards, and we have two independent variable, the score on maths and the program to which it's one is included to. So maths is the variable maths is a continuous variable, continuous predictor, because it can be any values, right? And the program to which a student is enrolled is a categorical one, because there are three categories: general, academic, and vocational. And we have coded one as general, two as academic, and three as vocational. You can code any way you want. It's just a matter of how you define your variables. Okay, so this is how we have done the coding for the categories. All right. So first you read the data. So that's the first step in any modeling exercise. And then there are several exercises that you will follow, right? We'll find the mean, the variance, the standard deviation, minimum, maximum, and so on. Now, one thing you might have seen in this data that I've shown you, that the number of hours, the dependent variable, is mostly zero, right? Because most students wouldn't have even earned a single hour. But there are few people who have 1 hour, 2 hour, 3 hours. So it's very skewed data. It's not very, you won't find this bell curve data in this case. You'll never find that. It's very skewed, okay? And technically, this is we call that as a problem of dispersion. We'll talk about that later point of time in this particular session. So we'll go ahead with importing the data, and then we'll do the exploratory data analysis to understand the distribution of the data, whether it's actually fitting a Poisson distribution or not. Just look at the mean and variance, and you will get to know if they're similar, and that's when you are sure that you are good to go with a Poisson regression model. Okay, given that we have a categorical variable, so we just do the factoring, and it's pretty much simple, like you might have done it in other modeling exercises. Just use, and those who are not familiar with, just use the function factor, and then do this labeling. Okay, so it's just to make sure that R understands your labeling properly, so that you can interpret your results very well. Once you have done all the exercises of analyzing data, and you're sure about the fact that you have you're going ahead with a Poisson regression model, use call the GLM function, okay, and use the distribution Poisson. So this is important, and provide the data set that you have reported. Okay, so we are using the family of distribution Poisson. So that means the function itself, the GLM function, will understand we are trying to call a Poisson regression model, and this will fit a Poisson regression model to our data, and then we'll summarizing data. You can do it in 2 steps. I've done it in just 1 step. Okay. Another important thing to remember is that okay, so I'm not going to get in the details of it, but I'll just give an example of it. Okay, the standard error that you automatically get from by fitting a GLM model is actually not correct. Okay, there seems to be an issue, and there is an academic reason behind it. Okay, it may not be as important in a real world, in a more applied sector, but theoretically or in academic setup there is some issues with the standard error, the way we do the estimation using the maximum likelihood estimation. Okay, because standard error is more to do with some sort of a distribution, and that's I'm not going to go into the details of it. Hence, you have to find what is known as the robust standard error. Okay, the normal standard error will not, or the normal standard error from a more like a normal distribution and multiple linear regression will not be very suitable here. So we'll find what is known as a robust standard error. So there are few steps to follow, and you can always read more about what robust standard errors are. I'm not going to explain to you, but if you might have come across robust standard error in other non-ordinary least square models as well. In fact, in my channel I have talked about it quite a few times. We'll not get in the details here. Okay, so these are the steps. I've given you the code. You can find out the robust standard errors through this. You can find out the lower limit, upper limit of each of these estimates. Okay, these codes to be followed. Okay, and you can use that. And I highly recommend you should actually go ahead and run through these run these steps or run this code in R to be able to understand it better and get a better feel of it. All right, so we have this result now. Okay, so we have run your model, and we also find out the robust standard error. Now given this, okay, so I'm not able to see. So this is the result. Okay, so I'm not able to see what the variables are. Okay, let me explain. This is the standard, this is the intercept. Okay, let me write it for you. This is the intercept. This is the score for maths. Okay, and this is the vocational, and this is academic. Okay, so we had how many factors? General, academic, vocationals, right? So vocational academics are given to us. This is compared with general, right? Like any factoring, you might have said, if there are 3 factors or 3 categories, there will be 2 estimates, right? There will be 2 estimates, and there will be 1 base. So the base here is general, and academic and vocational have been compared to that. Okay, so this is the intercept. This is the the beta values, the alpha and beta values. This is the the standard error, the upper limit and lower limit. Okay, the upper limit and the lower limit. Okay, ulta, I'm saying lower limit, sorry, the lower limit and the upper limit. Okay, great. So how do we interpret this? Now we have this result in place. We have the intercept, we have the slope coefficient for vocational and for academic. These are the category variable we have used, and we have also the estimate for the continuous variable, independent variable, which is score on maths. Okay, so how do we interpret? So the coefficient of math is 0.07. Okay, what does it mean? How do we interpret? In a typical multiple linear regression, we would have said that if we increase the score on maths is increased by 1 unit, okay, the corresponding increase in the dependent variable will be 0.07. But that's not the case here. How do we interpret this? The expected log count, or the log of the count of awards, because remember we are we are modeling for the count of awards, right? Number of awards won by the students. Okay, so if the score on maths is increased by 1 unit, the corresponding increase in log of count, not count, the log of count of awards is 0.07, right? Slightly trickier compared to a multiple linear regression, and I highly recommend to read this particular statement more carefully to understand. The coefficient of math is 0.07. This means that the expected log of count for 1 unit increase in math score is 0.07. Now we have got the indicators, 2 indicators, program academic and general, right? So that there is a comparison here. Similarly, you can explain these values, right? The way we interpret the categorical variable. Take that one as a base and compare the 2 other estimates to the base estimate. So we compare how somebody enrolled in academic program will do better in winning hours, number of hours compared to general program. Okay, similarly for a vocational program as compared to a general program, right? So that's the way you interpret. One important thing we are missing out here. In multiple linear regression, we always find what is known as R square, right? We have not talked about R square here yet, because R square is what will tell you the the best part of or rather what percentage of variation your dependent variable is explained by a set of independent variables. So that's not the case here. We can't have a R square like thing in Poisson regression model, because the fundamentals behind R square assumes that some sort of a different distribution. That is not the case in Poisson regression model. So you can't have a R square like thing here. There are some people who are using pseudo R square, pretty much like you have pseudo R square in logistic regression, but that can no way be explained the way you explain R square or adjusted R square in multiple linear regression. So how do you measure the goodness of it? How do you measure that efficiency of a model? Okay, so if you're doing a predictive model, so find out the root mean square, root mean square error. So that's one best way. So build a model in training data and test it in validate it in test data or hold out sample data, right? So that's one way of ensuring that you are doing it. Your model is performing really good or not. Okay. And also when it comes to interpretability, you look at the estimates, the signs of the estimates, and also look at the strength of the estimates, and you will also get a feel of whether the model is actually performing well or not. And always good to go with some metrics, so I would highly recommend to look at the root mean square error as well. Okay, some few important points to be remembered while building a Poisson regression model. So you should also always check out for the over dispersion. Over dispersion is basically related to cases where you have excess zeros, right? Because most of the students in a data sample who don't have won any awards, so there will be a lot of zeros there. The data itself is so skewed that it is over dispersed by a single value. Okay. So hence, you should always ensure that you have sufficient number of independent variables that actually explains this distribution. So you should not have this omitted variable bias, or you should not omit important independent variables. Okay, that's important thing to remember. You always need a large sample size because the estimation that you are doing is MLE, maximum likelihood estimation, and for that you need a large sample size. The interpretation is very tricky, as you have already seen. Both interpreting your estimates and interpreting the adjusted the pseudo R square is different from what we normally do in a multiple linear regression. So be careful about that. And remember one thing: the R square cannot be interpreted in a similar way than as you do in an ordinary least square multiple linear regression. And this is very useful in many real world problems. As I have already talked about it in the beginning of the session, there are a number of industrial applications, whether it's operation, in finance, in supply chain, in many manufacturing companies. You actually come across cases where your dependent variable is a count of something, and that's exactly where you should go ahead with modeling using Poisson regression models. So thank you so much, and if you haven't subscribed to our channel, please do subscribe, and also you can visit to our website. It's there in the description section. Thank you.